So the treatment for finite games is to define a natural extension for which we will be able to guarantee the existence of Nash equilibria. This extension is going to be defined for any games, but for finite games, for those, we will have all these Nash equilibrium. And the intuition is that it's basically a model of probabilistic behavior. What you do when you not play deterministically, but when you rather play according to some probabilistic distribution. And first of all, let's say that we define by capital delta S the set of all the probability distributions over S, over a given set. S can be finite or not. But if S is finite, let's denote it's 1 from K, just any K elements, then the probability distributions can be defined as a vector in R plus a length of K, such that the sum of the elements is 1. So it's basically a set of all the convex combination of K elements. And basically, we can say it's a way to concretely write out all the probability distributions over a K element set. Of course, the number of such distributions is infinite. It's uncountably infinite. And we say that 1 second. Okay. Such a distribution can be seen as a function. So since it gives some probability to each one of the elements of S, it can be seen as a function from S to R plus. And we call the support of P to be the elements which get strictly positive value, or in this sense, probability. Of course, you can check that this satisfies all the probability axioms, that is definition. And we call the support a set of all the strategies, or all the elements of this set. It will be strategies in the future, who have non-negative probability. So all the elements who play here, so to speak, they are called the support of this distribution. Now, given this general definition, now given a finite, no, not necessarily finite, given any strategic game G, it's important that we define it for any game, but we are going to use, of course, it mostly for the finite games, because that's why we have this famous Nash theorem. Now, for any game, we find a new game, which is always infinite, and which is called the mixed extension of the original game. So, the mixed extension of G is the game delta G, which is defined as follows. So delta G has all the players that G has, but the strategy sets are different. So the strategy set of delta G is a Cartesian product of the strategy set, which are probabilistic distributions over each one of the strategy of the original strategy set. So the strategy of the player I is not to choose something in Si, which she originally did, but to choose a probabilistic distribution on something she originally did in Si. So she chooses how she's going to randomize, which lottery is she going to have, and it's independent of what the other players do. And that is these are the strategies. So they can be said to model probability distributions. If they're going to talk a bit more in details what exactly this kind of model. And the utilities are simply linear extensions of the original utilities to the case of to this case, and we are now going to write exactly what we mean by linear extensions, but it's simply the expectations. And here actually we use the von Neumann-Morgenstern theorem, which says that the utility functions can be chosen such that they represent the preferences and the expectations, mathematical expectation, represent the preference over lotteries. Actually, that is when we need this theorem. That is the real use of the theorem. That it's not just a utility function, but a utility function whose expectation represents the expectation of lotteries. So delta SI is a set of independent probability distributions of SI, and these are called mixed strategies. So this is a mixed extension, and the game and the strategies in this mixed extension are called mixed strategies. And the original game is called either just a game or pure game, and its strategies are called pure strategies. If you don't say which, it's always pure, but when we talk about mixed, we can kind of juxtapose it with pure. And the new utility is the expected value of the original utility. So the utility of play I, when the probability profile is P, is the Lebesgue integral. That's a formal definition for any kind of probability for any game. That's the formal definition of expectation. The Lebesgue integral of the space of all the distributions of the utilities of concrete profiles with respect to those weighted by the concrete distributions. In the case of the finite game, and then the distributions are on the finite set, this Lebesgue integral can be simply written as a sum. So this expectation is simply equal to the sum of all the pure strategies. When we weight what the player gets in this pure strategy by the probability of that strategy, of that profile, not strategy. We look over all the profiles and we weigh what the player gets in that profile with the probability of that profile, which is from independence the product of the probabilities of the constituent strategies. So that's a natural definition of this probabilistic extension. And as I said, it depends on von Neumann-Morgenstern assumptions, because that's what gives us the theorem, which allows us to assume that the expectation of the utility functions will give us the utility function, which represents the expectations on lotteries. And then, having defined this mixed extension, let us make simple observations. So first, from the multilinear from the definition of UI as a linear thing, expectation, first follows multilinearity of UI in the sense that for any player, if we have a convex combination of two probabilities, B and C, and the rest do something A, then the utility in the mixed extension is equal to the same convex combination of the utilities of that player if that player just plays A against just plays B against A, and the other option is that it plays just C against A. And the second property is that for a finite game, we also can represent the utility of any strategy profile, any mixed strategy profile P, as the sum of the following form. We look at what the other players besides I. So for any player I, we look at what the others do, P minus I. But for the player I, we look at the concrete strategies, at the pure strategies, Si, and we look at the mixed strategies which can be basically identified with the pure strategies. So a E of Si, and we will need this notation for the future, is the following mixed strategy. So it gives weight 0 to all the strategies besides Si, and all the weight, all the probability is going to the Si. Si's place. It's not Si prime, it's Si's place. I should have changed it. It's a bad, it's confused, yeah? Yeah. Si's place. My apologies. So in the other places there is 0, and in the side place there is 1, because all the weight goes there. So this probability 1, that mixed strategy plays aside. So we look at what happens if the player plays with probability 1 Si, or gets the same mixed strategy of the others, P minus I, and we weight that with the weight that Si should have got Pi of Si. So instead of getting the Pi inside the U, the capital Ui, we can get it outside. That's simple again. That's from the linear definition of Ui. So we have these properties. And now we are getting closer and closer to proving the famous Nash theorem. Now we can first define what is a mixed Nash equilibrium. So a mixed Nash equilibrium of a game is a pure Nash equilibrium of the mixed extension, because the mixed extension is also a game. So as before, identifying is pure strategy with a certain mixed strategy, where simply with probability 1 the player plays this pure strategy, we can claim the following lemma. A pure strategy is a pure Nash equilibrium of the original game if the same strategy, simply the mixed strategy, which plays this pure strategy with probability 1, is a mixed Nash equilibrium of the, of course, so it's a Nash equilibrium of the mixed game, or of the new game, or it's a mixed Nash equilibrium. So strategy is a pure Nash equilibrium if and only if it's also a mixed Nash equilibrium. And it's quite simple to prove. So if there is a strategy which is a mixed Nash equilibrium, then the conditions that every ESI is an optimal reaction for others, they are the same as saying that SI is the optimal reaction for others. And even being the optimal reaction from a larger set is definitely implies that SI is an optimal reaction from the original set of strategies. So the conditions on the mixed extensions imply the conditions that it's a Nash equilibrium in the original game. And in the other direction, if you have a pure equilibrium, so a Nash equilibrium in the original game, then the linearity in the definition of capital Ui of the new utilities implies that the conditions for mixed attention also hold. Okay, so having proved that an equilibrium in the original game is an equilibrium even only if it's also an equilibrium in the mixed extension, we have basically shown that all the original equilibria are preserved in the new game. But maybe some equilibria get added, and that's the case sometimes. So a burning question is, if the original game had no equilibria, can the new game have no equilibria as well, or does it always get some equilibria? Well, the general answer is yes. The new game can be empty too. The new set of Nash equilibria can be empty too. But if the original game is finite, then the new game has at least one Nash equilibrium. And that's the famous theorem of Nash from 51, which we are going to prove. And before we prove, let us talk about the meaning of mixed Nash equilibria. And there are many opinions of what it can be done, of what can be, what it can be. And so not everyone, even scientists who are famous, not always agree on those meanings. But while the definition of what we mean by mixed Nash equilibrium is a formal definition, and the proofs are the proof things are facts, the meaning is at least it's not an exact scientific fact, but rather something from behavioral psychology which we can check, or even something which we can really check, but rather a philosophical approach, what we think that is. So it's not unusual that the meaning of mathematical or exact scientific result is contended. It can be controversial what it means, because only the result is a fact. So some of the ideas to interpret that are as follows. And there I've mentioned here some of the ideas which I mentioned in Osborne and Rubinstein, but there are several instant papers on that, and again, I think that the papers I read there are philosophical. It's kind of hard philosophy, in the sense that it's hard science. So not hard science, but it's kind of not the philosophy which is extremely soft science related. It's hard science related, but it's still not science. It's still philosophy. It's just related to hard science. So it's definitely something we can agree or disagree with. It's not necessarily a fact. So some of the ideas are that it can be that the probabilistic distributions are actually actual random actions that the player decides upon how she will randomize and then actually implement this randomization somehow. It can be that that unlike the analogical Nash equilibrium being a steady state where nobody has an incentive to deviate, if the others don't deviate, this is stochastical steady state in the sense that knowing what the others did in the past, I know what their expected frequencies are, and then what I do is the optimum, the best response to what they have been doing historically. In that sense, it's the stochastical steady state. And the idea that the reason that in the past the players played not deterministic student strategy, but in a way which play different strategy, can also be a result that maybe we just model a big population and every player models a certain population for which you just randomly choose a player who does something, an actual player. And another option is to say that there is a more complicated game behind the scene which we don't want to model explicitly, or we cannot model explicitly. And mixed strategies are basically pure strategies in that more complicated game. Another very famous model, very famous explanation is the following model by Harsanyi, who was a very, very famous game theorist, also one of the Nobel Prize laureates for game theory. I think it was formally economics, but he really did a lot of game theory. So he said that assume that the player relevant conditions are not fixed, that there are random perturbations, and you can only know what is the concrete realization of random perturbation about you. You don't know what happens with other players. In that case, the relevant solution concept is not Nash but Bayes Nash equilibrium, which we don't study now. But when you look at those perturbations getting approaching zero, then the limit of those can be modeled as a mixed Nash equilibrium. So Harsanyi tried basically to explain in a certain way why we can see certain plays, why we can see certain behaviors, and his model assumed that there can be perturbations which are random, and he did prove that there are results which relate equilibria and Bayes Nash and convergence and all that. We are not going to get into it. It's more complicated, but it's a very strong and famous theory which can be used, model and theory which can be used to back up what we do. Another model is from the point of view of epistemic game theory, so a game theory which talks about what we know and how that influences what we do and how that can get influenced from what we observe. And in that way, the whole idea of Nash equilibria and mixed extension can represent common beliefs which are consistent with common knowledge of rationality. So everyone knows that everyone is rational, everyone knows that everyone knows that everyone is rational, and so on. And if we model that it's simply the belief that that's what is reasonable to do, but that's not necessarily what you do, then it has less predictive power. But it is a reasonable way to explain mixed Nash equilibria. Okay, so these are all the options to explain what a mixed Nash equilibrium is. And let us now prove the famous Nash theorem that every finite game has a mixed Nash equilibrium. We prove the theorem not as Nash proof, because he used another fixed point theorem called Brouwer's theorem. And we prove that using what we basically proved based on Kakutani's theorem. So we eventually based what we do on Kakutani's theorem. And the proof is very simple, because we use Kakutani's theorem well. So for every player, the set of the mixed strategies is not empty, convex and compact. By the finiteness, it's compact. Otherwise, it's only non-empty and convex. The linearity of users implies it's quasi-concave, and it's also continuous. Again, here for continuity we need the the finiteness. And therefore, the existence theorem we proved based on the Kakutanis theorem proves the existence. So the proof we show is simple because we use another theorem which uses Kakutani. So we have several levels of interaction, but as computer scientists, I guess you are used to that. Well, as mathematicians, you can be used to that too. Simply mathematicians don't pay with computational overhead over interaction levels. So, and this proof uses finite, as I said, that compactness and continuity may fail if we don't know that it's a finite game. Moreover, the theorem is actually wrong when the game is not finite. But we can find another theorem. There are theorems which need more conditions, like the famous theorem of Grigsberg, who already in 52, so a year after Nash, had proved this theorem. Grigsberg proved another theorem which talks about mixed extensions of infinite games, but let us not go there right now. And let us now go to a proposition which is very, very important. It's quite simple, but it's very important in the study of mixed Nash equilibrium.